All right, thank you and welcome. This is the Introduction to Electrically Conductive Coatings, Paints, and Inks. My name is Jared Cohen. I am the Marketing Communications Manager for Parker Chomerics. I see folks are still joining our meeting, so we'll give them another 10 or 15 seconds, and then we'll get started. Thank you. All right, see folks have joined us, so we'll go over just a few housekeeping details before we begin. Please make sure you've set yourself on mute if you are not already. And after we run through the slides, we will have time for a live question and answer session at the end. So if you have any questions during the presentation, please feel free to type in that Q&A box down at the bottom ribbon there. You'll see the Q&A button. Go ahead, submit our questions, and our experts will get to them at the end. And then finally, don't worry if you maybe missed part of this presentation or you'd like to see it again. This will be recorded and sent to you shortly after the call. So with that, let's introduce today's speakers. We have Sierra, Ben Nudelman, and Brian Flaherty from Parker Chomerics. Sierra, are you there?
Yeah, hi everyone. Thank you for joining. My name is Sierra Eiden. I'm a mechanical engineer and I've been doing sales with Parker for over 10 years.
Hi everyone, my name is Ben Nudelman. I'm a market development engineer for Chomerics and I've been with the team for about 3.5 years.
Hello everyone, this is Brian Flaherty. I'm the Specialty Materials Product Line Manager. I've been with Parker for over 20 plus years, developing, testing, and selling a lot of these conductive materials that we're going to be talking about today.
So we'll start today with a brief introduction about who Parker Chomerics is. Then we'll get into the basics of what are electrically conductive coatings. We'll talk about their design considerations and how you may apply and work with those coatings. We'll talk about testing and validating, and sort of finally, what we think might be really most interesting to you, really get into some direct application examples of how some folks in the industries are using these electrically conductive paints and coatings and what that might look like in the field. And then finally, again, we'll get to that question and answer function at the end with our experts. So first, just a quick note about who Parker Chomerics is. Parker Chomerics is a division of Parker Hannifin Corporation, and we are the global leader in the development and application of EMI shielding and thermal interface materials. Our core competencies are in materials science and process technology. And Chomerics really does offer a market-driven product development cycle where we feature integrated electronics housings, and we're really proud to offer a custom engineered solution to all of our customers where we integrate our global supply chain management really for everyone's benefit. So with that, let's get into our presentation.
All right, guys, let's jump right in. There's a lot to go over today. Just to remind you, at any time you can add your question down at the chat feature in the bottom of the screen.
So to start, let's talk about the three main components of an electrically conductive coating. The first component is a base polymer, such as acrylic, epoxy, polyester, silicone, or polyurethane, and makes up the body of the coating. As with many other electrically conductive materials, the key conductive properties come from metallic powder fillers. These are many of the same fillers that are used in sealants, adhesives, and elastomer gasket, but often go through additional processing steps. And finally, coatings benefit from the addition of additives and solvents that can improve the adhesive properties, dispensability, and pot life. We also wanted to clear up some common misconceptions about terminology. A paint is technically a surface layer used to provide aesthetic benefits. A coating, on the other hand, is a surface layer that provides a performance benefit. These benefits can be anything from waterproofing to corrosion resistance, and in the case of today's webinar, EMI shielding and electrical grounding. By these definitions, every material and application we talk about today will be a coating. However, in common practice, the words paints and coatings are often used interchangeably.
And when we refer to inks, we're talking about material with a higher percent of conductive solids and a slower evaporating solvents. These solvents allow the ink to stay in a liquid state for a longer period of time to facilitate that screen printing application. Most coatings will have a lower solid content and faster evaporating solvents. And additives are compounds that improve the flow properties of the coating as well as the settling and dispersion of those metallic particles. Solvents are added to coating solutions to modify the sprayability and viscosity of the paints.
Lastly, passivation is a process of limiting the reactivity of metallic fillers in order to reduce the potential and the extent of galvanic corrosion. This passivation process uses organic coatings and particle development techniques to chemically reduce that reactivity.
So there's several reasons why you would look at using a conductive coating. Maybe your customer told you that your electronics package is overweight and it's cool to the functionality of the overall system. Maybe your multi-component circuit board has crosstalk between the chips. Maybe you just went through environmental testing and there's a mysterious powdery white substance all over your gasketed areas. These materials provide an electrically conductive shield for EMI and can be used for grounding. They provide added corrosion resistance to metal substrates, and they've also been used as in HIRF or high intensity radiated fields for airframe applications.
At the end of the webinar, we'll give some examples of specific applications where conductive coatings have been used, but this slide lists several of the generic categories. Coatings are used in nearly all markets and industries, from defense and aerospace to automotive to life science and telecommunications.
So additives are put into a coating solution and are meant to impact the rheology or the flow of the materials. Additives are meant to work with the various particle fillers and are used to hold those metallic particles in suspension for greater periods of time and prevent particle settling. Hard packing occurs when the particles sink and create a dense layer that separates from the binder system and can make the application process very difficult. In general, additives are added in very small amounts, usually far less than 5% of the coating solution by weight.
On the other hand, solvents are added in much greater quantities, usually anywhere from 30 to 70% by weight. Solvent blends of different evaporation speeds are used depending on the properties of the application and the specific design constraints to modify the drying time and curing time for each solution. For example, a self-leveling application would require slower evaporating solvents to allow the material to flow and settle properly. In the same vein, solvent evaporation rate can have an impact on final surface roughness as well as the viscosity of the paint during spraying. For example, overhead applications will require less dripping. Finally, in some instances, such as acrylic binder systems on plastic substrates, the adhesion properties are based on the solvent actually attacking the microscopic surface layers. A stronger solvent, such as MEK, can be mixed into a paint solution to attack the plastic and allow for greater adhesion. Now we'll dig down deeper into factors to consider for your design. As a reminder, we will be answering questions at the end of the webinar, so please feel free to submit them throughout the presentation.
So I've said it before many times to engineers, and I'll say it here for you, but I do believe that everyone should get into the habit of hardening your system for EMI up front. And that is basically the best thing you can do. For EMI coating solutions, there are several categories to consider for your design. The electrical properties, such as EMI shielding or conductivity, are always a primary concern and can impact overall cost. The polymer-based material should be chosen based on the type of substrate, the operating temperature, chemical resistance, and other requirements for coatings can include UV protection, impact or shock loading, and wear limitations. These issues can come back fierce and can really add complexity to fixing your design when and if it fails EMI and you didn't consider these things up front.
A few of the mechanical considerations to consider when planning conductive coatings are adhesion strength, coating thickness, and flexibility. Adhesion strength is important to consider because not all polymer binder systems will adhere well to various substrates. Oftentimes, surfaces must be prepared with primers, adhesion promoters, or physical and chemical etching that we will discuss in more detail later in the webinar.
Yeah, and Ben, I'd like to add a word of caution on that note. When you consider using a chemically resistant plastic, that means that the plastic will resist the chemical coating. So I've seen these parts get sprayed and then literally the paint is dripping off and not adhering. So on that, coating thickness is referred to as a dry film thickness because the paint thickness is measured once all of the solvents have been evaporated off during the curing process. Coating thickness is impacted by particle size as well as the accuracy of the painting process, and in addition to the surface protection qualities of the recommended thickness of the paint, the coating thickness also has an impact on the electrical properties and really should be measured and validated to ensure proper performance.
And finally, different binder systems will have varying levels of flexibility. Some applications will have unique and complex geometries that will require less viscous paint to fill in tight angles and small crevices. Greater coating flexibility is a benefit on substrates that are subject to thermal expansion and contraction, as well as intended or unintended flexing or bending.
So because we're talking about conductive paints, we need to know about the electrical properties. Lower conductivity filler systems are often associated with lower levels of shielding and more cost-effective solutions if the shielding requirements are moderate. But as with other solutions, the overall conductivity is driven by the individual particle conductivity as well as the level of fill in the paint. So coatings need that even distribution of the fillers throughout the part to make sure the entire surface has the ideal properties.
On a very important note is that EMI shielding is not always directly correlated with particle conductivity. Let me emphasize this. High conductivity particles will provide good EMI shielding, but low conductivity particles can also provide very good EMI shielding because of factors such as particle shape, particle size, and paramagnetic or ferromagnetic properties. These properties will actually impact the shielding at lower ends of the frequency spectrum, specifically in the magnetic field range.
And finally, galvanic corrosion applies when the material with the different electrical potentials come in contact with each other and in the presence of an electrolyte, such as salt fog or atmospheric moisture. When conductive coatings that have particles such as silver, nickel, and copper, these are bound to be voltage differences within the aluminum, the titanium, and the steel substrates. So fortunately, there are steps we can take to reduce the reactivity of these conductive parts.
Finally, we wanted to talk about environmental considerations. The environment in which the coating is operating will have an impact on lifespan and performance. For example, all paints have an operating temperature range that is mostly driven by the temperature limits of the polymer binder. Epoxies will have a higher maximum operating temperature than acrylics, and many polyurethanes will actually be able to operate at lower limits than many others.
Likewise, different polymer systems will have different resistances to harsh chemicals and fluid washdowns. So most coatings will hold up well to harsh chemicals, but are often paired with a non-conductive top coat to protect them from varying environmental conditions. So corrosion resistance is a concern when coatings are exposed directly to the salt fog or corrosion-inducing environments.
We wanted to provide you with a basic summary of coating polymer properties and how they compare based on some mechanical and environmental factors. So, for example, as you can see, acrylics tend to perform at a lower level in most of these metrics compared to other polymer systems. This doesn't necessarily mean that they cannot meet program requirements, but we often see acrylics used in applications that may be protected from the environment or in places where temperatures are more controlled. Likewise, epoxies have fantastic strength and temperature resistant properties, but are not recommended on substrates that may flex or bend or undergo vibration because of their brittleness. For such an application, polyester-based paints may be the best solution.
Okay, so now we're going to get into working with conductive compounds and what it takes to apply them. This section's the longest and most thorough of the webinar because of the importance of many of the factors in working with coatings and achieving the best performance. First and foremost, safety first. Safety must always be a concern when we're working with these coatings, and not only should you and your EH&S teams review the material safety data sheets, but you also need to understand the OSHA regulations when you're working with and disposing of these coatings. So proper PPE should always be used, and because nearly all coatings are solvent-based, they should only be sprayed in well-ventilated areas and under a fume hood.
VOCs, or volatile organic compounds, as well as hazardous air pollutants, or HAPs, are the gases emitted when spraying coatings and are contained in different amounts in each type of coating. Some solvents are actually considered exempt materials by the EPA and therefore are not included in the VOC calculation. In this case, these exempt materials can be used to formulate coatings with lower VOC content to meet company environmental requirements. Examples of these exempt materials can include acetone or PCBTF. In many cases, licenses or permitting may be required for organizations that are dispensing coatings and releasing large amounts of VOCs.
And of course, before any coating is applied, there are several steps to take when preparing the surface. At the very least, you need to clean the surface and keep it free of any oils, dust, dirt. Just like with conductive sealants and adhesives, primers and adhesion promoters can be used to provide those best adhesive properties. So the important difference between adhesion promoters and primers is the application method. So in general, primers are sprayed onto a surface, while adhesion promoters are typically wiped on with a clean cloth.
Surfaces may need to be physically roughed or chemically etched so the materials adhere well. Physical surface treatments can include things like sandblasting or wet sanding. Flame treating and oxidizing surfaces, as well as conversion coatings, can help reduce the electrical contact resistance. And finally, as we've mentioned in previous webinars, corona surface treatments or arcing of the material will actually align charged particles on the surface of the material and encourage strong adhesion, but should really only be done very shortly before the application for best results.
Masking is another important step when you're applying these conductive coatings onto your housing. We just want to briefly mention the importance of making sure that the paint is applied to all the edges that will come in contact with your EMI gasket or other conductive surfaces. So using a non-conductive gasket mated up against a conductive paint will defeat the whole purpose of the coating and open up your design to EMI susceptibility. So as you can see here in our very excellent artwork, there are a few different solutions to properly mask surfaces. In the center, you see a properly masked and sprayed part with the conductive coating aligned with the EMI gasket. On the left, you have a combination environmental and EMI gasket for those very harsh environments, with the coating lined up with the conductive interface points. And on the right, we show a part that has overspray of the paint. And it's important to note that the overspray is not going to have any detrimental performance properties, but it may impact the aesthetics or add cost if the coating is used in high volume. So Ben, any other things that would be good to point out here?
Yeah, I wanted to mention that complex parts can require fixtures to be created for ease of masking the parts. And actually, more importantly, the masking tape that's used should be checked to be compatible with the solvents in the paint. So if the tape is not compatible with the solvents, those solvents can actually eat away or soften the tape and the adhesive on the masking. This can create a pretty big mess and actually limit the clean lines that the masking would typically add. One of the biggest and most significant differences in working with conductive coatings versus non-conductive coatings is the proper mixing of materials. Because conductive coatings consist of very heavy metallic particles suspended in a solvent and polymer base, the paint needs to be mixed on a paint shaker for at least 3 to 4 minutes before spraying. It can also be mixed by hand with a large spatula, but should be a completely homogeneous suspension before you start the spraying process. At the same time, the paint should be constantly mixed and agitated throughout the spraying process, probably every 30 to 60 seconds at least. The real key is to make sure that no unmixed material remains on the bottom or sides of the container. Just as important as mixing the paint well is mixing it per the proper instructions from the manufacturer. In multi-part or multi-component coatings, the parts must be mixed in a certain order or method.
Yeah, acrylics tend to be a one-component solution, so this would have less of an impact. But epoxies are typically two-component, and polyurethanes are often 3 or 4-component solutions. So different paints will have different weight particles. Heavier particles will sink faster. Those need extra mixing. But the most important driving factor for the mixing is that if the particles fall out of suspension, the paint will not give you the ideal electrical properties that you're looking for.
A few additional definitions to include when talking about the application of coatings: pot life and working life. Oftentimes, these two different types of time measurement will be included on the manufacturer datasheet.
Pot life tends to be a more technical term and is defined time during which the viscosity or the thickness of the mixed system doubles. This is an effective measure for comparing coatings and understanding the solvent characteristics of a coating.
Working life is a more application-specific definition and is the measure of how much time you have to apply the material before it reaches such a state where it cannot be worked with. In some cases, the pot life will actually be shorter than the working life because a coating that has doubled the viscosity may still be able to be applied effectively.
Conductive coatings are formulated to be applied via a spray gun, and in most cases, you should not brush these on. The main reason for this is the even distribution of the conductive particle flake technology. So these flakes are meant to lay flat and be present in equal distributions across the entire surface. Each coating should be applied to a specific wet layer thickness, which will eventually dry or cure to a dry film thickness. And in some cases, several thinner wet layers are needed to achieve that correct dry film thickness. So in each case, the paints or coating are applied in several box coats.
Box coating is the process of overlapping previous spray application passes and then applying a similar motion at a 90-degree direction change. This ensures even coating and a limit of the directionality of how the paint lays down. To calculate the theoretical coverage and the cost of an electrically conductive coating or paint, you'll want to note the percent volume solids of the material the manufacturer notes on the technical data sheet.
Yeah, so for example, the theoretical coverage of a 1 gallon of paint at 100% volume solids at the manufacturer's recommended thickness, or called dry film thickness, or DFT, of 1 mil is expressed as 1,604 feet squared at the DFT.
So taking that formula, if I had a gallon of an electrically conductive coating with a 30% volume solids and a DFT of 1 mil, then the theoretical coverage of that gallon of material is 481 square feet. Theoretical coverages of paints and coatings do not typically include any overspray or material scrap in their calculations. So it's important to note that that is basically just an approximation.
Is it possible to calculate the theoretical coverage of a conductive paint given only its weight percent solids?
No, and it can actually be difficult to estimate given the various metal fillers used in conductive coatings. The best way to compare the cost of conductive coatings is by calculating the applied cost of each material.
Yeah, and to figure out the cost for the material for each of your parts, you must take into consideration the price per gallon of the coating, the area of the part that you're painting in feet squared, the manufacturer's recommended dry film thickness, DFT, to achieve the coating's mechanical and electrical performance. Theoretical coverage of conductive coating assumes a full gallon, which is not always the case, so take that into account. And then you should estimate kind of overspray and material scrap for conductive coating during application are important as well. And some people just add a percent, 5-10% scrap. So in general, we've been speaking about coatings, but we wanted to briefly touch on conductive inks. So with inks, the most important differences to consider are slightly different from the conductive coatings because of different performance requirements and basically different application methods. So typically you see inks applied as printed electrodes. They're used in life science application for biometric sensing technology, or simply as a method to carry current from one place to another. Therefore, the viscosity of the material is very important. So when screen printing conductive inks, pitch and thickness of the printed lines will vary, obviously, and then the mesh screen openings per inch will actually depend on the conductive filler particle size. So you want those little flakes to make it through the screen and onto your substrate. And in addition, you also want to consider whether those printed electrodes will be coated with or applied onto a dielectric or insulating material.
As a quick summary, we wanted to review the three main processes of working with coatings: mixing, applying, and curing.
Mixing can be done by stirring or shaking and should take into account particle densities, manufacturer's recommendations, and mixing time.
Applying paint should always be done by spray application and preferably in a box coating method to limit directionality of the paint. Inks, as we just mentioned, are applied using screen printing, and the application consideration would be the openings per inch on the mesh.
And finally, we wanted to talk about curing. So all coatings are able to cure in room temperature conditions, but many have elevated cure cycles that can cure the material faster. So in most cases, the higher the heat, the faster the cure, but there are obvious upper temperature limits to things like your plastic housing and the material itself. So it's also very important to check the temperature limits on the substrate that are sprayed, especially plastics. Many paints can be cured at temperatures that will damage the plastic substrate and should obviously be avoided.
And a very important note, for elevated cure temperatures, the highest recommended cure temperature is usually the one that will give the best mechanical properties. Oftentimes, coatings will need to cure for a short period of time at room temperature to allow for the solvent evaporation before being cured at a higher temperature for those final mechanical properties.
Equally important to discuss what to do versus what not to do and why. And there are pitfalls and challenges to applying a proper coat of conductive coatings and inks. These challenges don't just make it look bad, but they're bad for the functionality of the material itself. So Ben, what happens if the surface has inconsistencies in the look and finish? And why would it be bad if the coating looks shiny in one area and dull in another?
Sierra, that's a great question. And we had a customer call and told us that after painting their substrate, it had actually failed EMI testing. We were able to take a look at the photos that they sent and could deduce the problem right away. They had a very experienced paint operator who unfortunately had never actually worked with conductive coatings before and was unaware of the mixing requirements. When they sprayed the paint, the heavy particles sunk to the bottom, and some of the particles actually got sprayed out in clumps across the surface area. Coatings typically have flake-shaped particles and are meant to lay flat, thus coating the entire surface to block and shield EMI.
And on a similar note, Ben, we actually had a customer who had prior experience with applying conductive coatings, but we had supplied a new material with a heavier particle that sank faster than the other types that they had worked with. So they were getting inconsistent results for electrical resistance. And just, main point here is don't hesitate to ask. We're the experts and we'd love to help.
Our last section before application examples is testing and validation of materials. Volume resistivity, shielding effectiveness, adhesion strength, and viscosity are the key properties that most people test for to validate material compliance. Each has a different test procedure and often an industry spec associated with it, such as IEEE, ASTM, or military specifications. Volume resistivity serves as the most common electrical measurement for conductive coatings and is the basis for most performance comparisons. It's measured using a resistance probe and requires a simple calculation based on the dry film thickness of the paint and the surface area covered by the electrodes on the probe. With the relative simplicity of the volume resistivity test, it's actually often conducted before and after environmental and chemical exposure tests. Coated parts can be run through all kinds of fluid exposure and then tested for volume resistivity to ensure that the coating will maintain EMI shielding or grounding performance after long-term exposure in harsh environments. Examples of some of these fluids include jet fuels of various grades, hydraulic fluids, PAO coolants, strong solvents such as MEK, as well as long-term salt fog chamber exposure.
EMI shielding testings for coatings is very similar to that of sealants, gap fillers, and gaskets. A coated test panel, and often one that has undergone chromate conversion coatings per mil spec 5541 prior to coating, is run from low frequency testing at or below 30 megahertz to 10 gigahertz and higher for thorough testing. This test setup you see on the slide is a modified version of the IEEE 299 EMI shielding test.
Mechanical properties are tested using a whole range of industry standards. For example, adhesion testing is coded on coatings less than 5 mils thick is done using a cross-hatching tool to perforate the paint layer and then using a pressure-sensitive tape to pull against that cross-cut lattice and determine how effectively the coating will remain on the substrate without flaking or peeling. Abrasion resistance testing uses 2 rolling abrasion wheels on a plated test specimen to determine the number of cycles until a certain coating mass loss or until substrate exposure is achieved. Viscosity is measured using a Zahn cup. Each Zahn cup numbers 1 through 5 has a different sized hole in the bottom for different thicknesses or viscosities of material. The cup is filled to the edge with a coating or paint, and the solution is then allowed to start flowing from the bottom of the cup. The time is measured until the steady stream of paint flowing from the hole is interrupted and is then recorded. The time is known as the efflux time. Other tests include pencil hardness, wet density measurement, and pot life, as we touched on earlier.
All right, now we get to go to some actual examples that have worked in the field. So conductive coatings can be used in a variety of unique ways, and we're going to talk about those now.
The first application we wanted to present is an airframe graphite composite structure painted with a conductive coating to enhance electrical conductivity. For a number of reasons, including but not limited to weight savings, the customer chose a graphite composite on parts of an aircraft structure. They used an electrically conductive coating as a seed layer for electroplating, as well as to increase the electrical conductivity. Slightly related to this application is actually this process used within other industries, such as the automotive aftermarket. A conductive coating was applied to as part of a multi-step process for custom chrome parts, and was actually able to reduce the number of stages that were required for that plating process.
So this was a good program to work on. It was the customer's first attempt before the great miniaturization period of the early 2000s when everything was getting so small. But this was new to market technology that made their headset very attractive to the military, but they had never had to pass mil standard 461. So unfortunately, they went in with no shielding whatsoever and they failed. So they called us and we suggested a few different options. One was a small engineered laminate or copper foil origami, as I like to describe it. And although it was lightweight, it was labor intensive to wrap around the circuit board. Conductive plastics were suggested, but they didn't like the aesthetics. So the win was silver filled polyester paint. It solved their interference issues. It was lightweight, and it actually surprisingly improved some other features like noise canceling because it reflected outside frequencies. So through performance gains and cost reductions, they ended up using this electrically conductive silver-filled polyester paint and a mating elastomer gasket for EMI sealing.
Expanding into other industries, we've actually worked on several satellite dish applications for customers in defense, aerospace, and telecommunications market segments. In this particular application for a commercial satellite dish, the coating would be applied in a high volume to provide incident electromagnetic interference protection and would need to withstand long-term UV radiation exposure all over the globe. So an acrylic-based coating with a nickel filler actually met all of the electrical properties. And because it was a high volume application and because of the environmental application, it was actually combined with UV radiation protective top coat for that environmental exposure.
So this application for a shipboard door was in conjunction with a conductive elastomer gasket. So keep in mind the specific family of polyurethane coatings are meant to be painted onto metal to reduce corrosion. So the gasket was seeing harsh environments and fluids and was corroding and pitting the mating aluminum door frame. So the purpose of the gasket really is to be the sacrificial part of the stack up because you should expect some level of corrosion when you're mating metal filled things together, but you'd rather replace the gasket than the large aluminum frame. So the aluminum substrate was primed and then painted with the copper filled polyurethane. And that stack up was mated to the gasket for added protection in EMI. And the soluble chromates in the coating passivate the aluminum substrate, and the hydrophobicity of the material reduced the electrolyte present. So making it was more of a belt and suspenders approach. If you're interested in anything further on corrosion, you can always see our previous webinars that we did.
We really want to emphasize the CoShield 2000 series of paint because of the formulation and testing that has gone into creating an incredibly robust and effective material. From the hydrophobicity and the durability of the polymer binder to the passivation and the high electrical performance of the copper filler, this is truly a full service solution for nearly all military and defense applications.
Okay, still time to submit your questions, but before that, we just wanted to show you a list of some of the Chomerics standard offerings for conductive coatings.
While what you see on the slide are many of our standard options with various combinations of binder and filler, we did want to emphasize that we have a lot of control over formulation and new material development. This development can include reducing VOCs, changing component numbers, and performance or substrate compatibility. So again, here on the slide, you'll see a number of the different standard conductive coatings with binder and filler combinations and some common applications. But again, there is a lot of control on our end from the particle technology and the binder technology and the combination of those two.
Yeah, if you don't see it on the list, just ask. Okay, time for questions and answers. I guess I'll go first, Ben.
After you.
All right, guys. So we did have a couple questions come in before yesterday. So I'm going to read those. I'm going to start with those now. We had a question from Brett. Does the material being coated affect the electrical conductivity performance, or does the coating perform independently of the surface? So I don't know if we want to have Brian step in here on this, but.
Sure, I'll grab this one, Sierra. So part geometry definitely can influence the conductivity of conductive coatings, particularly parts that have sharp corners. They may have deep recesses where it's difficult to get in there and spray a uniform conductive coating. Also, parts that have very sharp geometries or very small features, depending on the particle size that's in the conductive coating, may be difficult for that particle size to go across, sharp corners or very tiny geometry. So yeah, certainly part geometry must be taken into consideration when you're spraying and applying these conductive coatings. It's also a good idea to measure the conductive coatings in those areas because those will typically be the weakest part of the EMI shield.
So the next question we have comes in from Joseph, and it's regarding some of the testing of the volume resistivity measurements that we have on our paints and coatings. So the question is, I'm especially interested in details of making resistance or resistivity measurements on small parts with non-planar geometries. Are there COTS 4-wire probes, or do I have to develop my own? And then talking a little bit more about what about taking the conductivity between two separate surfaces that have a conductive coating on them?
So that's a challenge. I am not aware of COTS measuring equipment for measuring difficult geometries for the surface resistance of conductive coatings. Chomerics does provide a co-probe, which I think we showed on slide number 30, which is basically 2 aluminum plates which serve as electrodes that are separated by a Delrin or non-conductive plastic to give you an ohms per square measurement. We have 1-inch co-probes as well as half-inch co-probes, which may be easier to use on some of those smaller geometries. But yeah, for something with large radiuses, they're going to be difficult to measure with the co-probes as well. So typically what I see our customers do is use some sort of 4-wire probe and come up with either custom electrodes or buy something, off the shelf from McMaster-Carr or Granger, one of those guys, to make their own electrodes for measuring those areas.
Okay, so our next question comes from Jim. Do these coatings conform to any commercial or military specifications?
Yes, so several of our coatings have been qualified to different military specifications. If you have a particular military spec that you're looking for a coating to be certified to, it's certainly a question that you can call and ask our applications department of whether Chomerics has a coating that is certified to that particular standard.
The next question comes in from Joseph, asking about specifying the adhesion properties of a coating. So he specifically says that there may be some subjectivity to ASTM D3359, which is that cross-hatching test that we mentioned a couple of slides earlier. Brian, have we done work with other adhesion tests or adhesion properties or requirements that customers may have?
We have, basically, they're very similar to that ASTM test method where there's some sort of scratch of the coating and some sort of tape used to quantify the amount of coating that flakes off after a certain amount of time. It's been evaluated both in a dry and a wet type of environment. There is some subjectivity. I agree with the questioner that there is some subjectivity to those tests, but we found here at Chomerics that the requirement for most of our customers is 4 or 5B as measured on that ASTM method, and that's 95 to 100% adhesion of the coating, and that's pretty easy to discern. I think you get into trouble when you try to say whether it's 30 or 40% adhesive failure. If you get something that's 95 to 100% at good adhesion, then it's pretty easy to look at that, and it's not as subjective when you're talking about that level of adhesion.
Okay, and then we have a two-part question from Mark. What temperature ranges are these suitable for, and how long is a cured coating expected to be stable in situ or stay on a system in storage? So how long are the coatings expected to last and what temperature ranges? So
yeah, so the temperature range really depends on the polymer and the filler in the particular conductive coating. Some of our silver copper filled coatings, CoShield 2056. Once you get up to higher temperatures, you can start seeing the silver copper filler oxidize and see some degradation in the electrical properties. But silver fillers will not show that same degradation at those higher temperatures. And when you're talking about from the polymer standpoint, some acrylics and urethanes don't have that high temperature resistance that epoxies may have, right? So it really depends on both the filler and the polymer of the particular conductive coating.
So the next question we have is from Malachi, asking about, are acrylics brittle? I know that's more of a subjective question or a relative question. Brian, if you want to weigh in on that.
They certainly can be, right? One of the things about acrylics, I mean, there are many different types of acrylics, like anything else. In general, I think that's probably a true statement. One of the things that most people like about acrylics is they're very durable. And, with that durability comes a certain amount of brittleness. Speaking of, in regards to Chomerics conductive acrylic materials, we actually use a blend of acrylics that have different hardness or brittleness. Some are more flexible than the others. And that's one of the reasons that we formulate with a blend is to have, that optimum, durability, but also have a little bit of flexibility so they're not too brittle. You don't want your coating to chip or crack easily.
okay, and we have a question from Anonymous. Will the cure cycle for the CoShield 2001 have any effect on moisture penetration?
So typically with cross-linking systems like the CoShield 2000 series polyurethane, the higher temperature you cross-link these materials at, the better the mechanical and electrical properties, just in general. So based on that, you would think that if you cure it at a higher temperature, you may have better cross-linking and better hydrophobicity of the coating. But because the polymer we use in the CoShield 2001 is hydrophobic in and of itself, I don't think that the degree of cross-linking would have a major effect on the hydrophobicity of that coating, that particular coating.
So the next question we have comes in from Steve, and staying on the topic of our CoShield 2000 series paint, he asks, the second to last slide had 3 coatings for military environments, all with a copper filler or that passivated copper filler. Can you briefly go over the differences? So just to start off that question, Steve, that those 3 paints are part of our CoShield 2000 series. And I will say that beyond those paints, a number of our other coatings, I should say, have been used in military applications and defense applications. Really just depends on the program requirements. So Brian, if you want to go into a brief explanation of the difference between 2001, 2002, and 2003.
Yes. So the main difference between CoShield 2001 and CoShield 2002 are soluble chromates. 2001 have soluble chromates. That was the original 2000 series paint that was developed. It provides the best corrosion resistance of all of our CoShield 2000 series coatings. The reason it provides the best corrosion resistance is because those soluble chromates will actually get absorbed up into the aluminum substrate. So even if you have a scratch or a chip in that CoShield 2001 coating, because the soluble chromates are there, they'll provide some corrosion resistance to that bare aluminum as it's exposed. CoShield 2002 was developed as a non-chromate version of CoShield 2001. So chemistry is very similar. It just doesn't have the soluble chromates. So as long as the coating is not chipped or scratched and there's no bare aluminum showing, it will provide just as good corrosion resistance as the Koshale 2001. And then Koshale 2003 is simply Koshale 2001 color matched. One of our customers came in and was looking for a darker Koshale 2001 material. So Koshale 2003 has the soluble chromates. It has the same performance as the Koshale 2001 from a corrosion resistance standpoint. It's just a different color. It has a darker brown color.
Okay, and this question is from Catherine regarding outgassing. Are there specific products designed for low outgassing applications?
I don't think we have in our product portfolio of conductive coatings, low outgassing coatings. It's something that we'd certainly look at if someone's looking for a low outgassing conductive coating. It's something that I could bring to our chemists and see if that's something that we could do. I guess I would ask if that is the case and someone's looking for a low outgassing coating, is kind of define what they mean by low outgassing, right? I mean, there are different tests and different standards depending on the application. And it's important to know that information up front before we take on that type of development effort.
Yeah, and I apologize, Ben, this was more like a 3-part question, so I'll just ask Catherine's other 2 questions in a row. So regarding edge flaking concerns during masking removal, are there other recommendations such as specifying time to removal?
Yeah, so that's a great question, actually. A lot of people see that flaking and cracking of conductive coatings depending on the type of coating, the type of cure schedule that you're using, and the time you take to remove the masking. Typically, if possible, I recommend that you remove the mask when the parts are wet. It's not always possible depending on your application, when the paint is wet. It's not always easy to do depending on your application, but that will give you the cleanest break. Once you start waiting for the conductive coating to cure, there may be some pulling or flaking of the coating if you wait too long. So it's really something that should be developed during the development of the application process, right? I mean, the masking, spraying, and removal of the masking is all part of that application development process that must be optimized before you go to manufacturing.
Good point, Brian. Okay, and then the final for Catherine. Regarding accelerated curing beyond temperature, are there specific humidity conditions?
Yes, and again, that depends on the particular conductive coating system or the polymer system. Acrylics really have issues with high humidity environments. If you try to spray our conductive acrylic coatings, Koshale 2056, Koshale 2040, or Koshale 2044 in high humidity environments, what you'll see is a blushing of the paint. It's this, you'll get like this white layer on top of the paint, and that's actually, moisture being absorbed up into the paint from the atmosphere because of the high humidity. And you'll actually see a measurable difference in the surface conductivity of those types of coatings if sprayed in high humidity environments.
The next question we have comes from Jim, and he asks about aluminum parts requiring a pre-treatment before coating. So Brian, I don't know if you want to get into some of the additional details beyond what we covered in the webinar here.
Yeah, I mean, again, it depends on what your goal is for the conductive coating or what type of environment the aluminum parts are going to see. If you're looking for, optimum corrosion resistance, then yes, I do recommend, doing some conversion coating before you apply a conductive coating. It always helps, the conversion coating can always help with corrosion resistance in case the conductive coating gets chipped or cracked, and having that extra layer of protection always helps. And if you're talking about coating the aluminum substrate for adhesion purposes, that again depends on the type of conductive coating and the type of adhesion that you require. Sometimes you need either a sprayable primer or, an adhesion promoter that you might wipe on that aluminum surface to try to optimize or improve the adhesion of the conductive coating to that surface.
Okay, and I know Michael has a couple here, so let's get his going. Is there a coating that can aid in X-ray resistance should lead shielding prove inadequate? Well, that sounds bad.
Yes. That is one that I would defer to some of our chemists. I'm not familiar with X-rays and what type of coatings might block that. I mean, we don't have an off-the-shelf solution that I don't believe, but that's certainly a question that, I will bring to our application, some of our technical people. Maybe we can get Mike's contact information. We can reach out to him after we've conferred with some other technical people to see whether that's something that any of our current conductive coating formulations may help with, or whether that's something that we could help develop a custom coating for.
Yeah, we'll reach out to you, Michael. We'll follow up.
A question from Malachi asks, how do the coatings compare to 360-degree coating? For example, a solid piece of metal. So basically, if we were to take a non-conductive or a less shielded material, paint it or coat it with a conductive coating, how would that compare to something like a stamped metal can or a metal chassis?
Typically, depending on, it really depends on how you're sealing that, right? I mean, if you're talking about, a true Faraday cage where it was completely sealed, piece of metal, then yes, that would obviously be significantly better shielding performance than our conductive coating. But if you're talking the difference between, a stamped metal can versus a silver-filled conductive coating on a piece of plastic, if it's sealed well over the chip or over the at the edges, then you can see similar results. We've got some shielding tests that we've performed on some of our board level shielding coatings like CoShield 604 that show, that silver filled polyester filled coating, conductive coating, shows or shields very comparably to a stamped metal can.
Okay, I think we've got time for one more, and it's a simple one from Michael. How does primer stick, Brian?
So we have primers and we have adhesion promoters, right? So in the industry, most people think a primer is something that you spray onto a surface to improve adhesion, and a primer is something that's wiped on. So typically the primer or adhesion promoter, most of them typically dry. They're, usually they're a mixture of solvent and silanes to improve the adhesion of conductive coatings, and they typically dry on surfaces as opposed to cure. There are some curing primers out there, depending on the chemistry, the primer chemistry, but a lot of the adhesion promoters are simply dry and do not cure. Hope that answers this question.
And with that, we wanted to thank you all for watching and participating in this webinar. Hopefully it was valuable to you all. And again, as you see on the slide here, you have the contact information for Sierra and myself. So please don't hesitate to reach out with additional questions. We'd be happy to connect you with Brian or the right resources that we have internally. Additionally, one last thing that we wanted to mention is the next webinar that we have as part of this specialty materials conductive gaskets and conductive coating series is in about a month and a half in the beginning of June. Specifically a webinar on our introduction to form in place electrically conductive gaskets. So be sure to look out for additional emails on that. And with that, thank you all very much.